All right, today we are diving into the absolutely incredible world of prokaryotic gene regulation. We're going to see how something as simple as a bacterium can manage its own DNA with an efficiency that would make any modern engineer green with envy. And we're going to do it all using what I think is the perfect analogy, a very, very smart kitchen.
So let's start with the big question, the central puzzle, really. A single bacterium, right? It has thousands of genes. Think of them as recipes in a giant cookbook. Now, making every single one of those recipes, or proteins, all the time, that would be a colossal waste of energy. So how in the world does it decide which recipes to cook and when, so it can stay alive and thrive without completely burning out?
Well, the secret all comes down to controlling this one fundamental process, the central dogma of biology. You've got DNA, which gets transcribed into RNA, which then gets translated into a protein. Now, every single step you see here, every transcription, every translation, it all costs the cell precious, precious energy. So if a cell is going to be efficient, it has to get a grip on this assembly line at the earliest possible stage.
And this brings us to the most basic controls in our smart kitchen. To manage that tight energy budget, bacteria have evolved this brilliantly simple system of genetic on and off switches. First up, you have the promoter. Think of the promoter as the main on switch for any genetic recipe. It's a specific bit of DNA that basically waves its arms and shouts at the cell's master chef, an enzyme called RNA polymerase, and says, hey, over here, start cooking this one right now.
But what if you don't want to make that recipe right now? Well, that's where the operator comes into play. The operator is like a safety lock that snaps right over that on switch. A special molecule called a repressor protein can come in and bind to the operator. And when it does, it physically blocks the chef, that RNA polymerase, from even getting to the recipe. It's the off switch. It's the nope, not gonna happen control. And yeah, this image just nails the concept. Together, the promoter and the operator work just like a simple light switch. You've got the promoter for positive control, turning things on, and the operator for negative control, shutting them right back off. It's this beautiful, simple, binary system that's at the very heart of gene regulation.
Okay, so using these switches, bacteria basically sort their genes into two main categories. First, you've got inducible genes. These guys are normally off. Think of them like a fancy waffle iron in your kitchen. You only bother to turn it on when you're actually in the mood for waffles. Then you have repressible genes. These are normally on. They're like your refrigerator, always running in the background because you need it, but you can turn it off if you really have to. So if controlling one gene at a time is smart, controlling a whole team of related genes all at once, well, that's just next-level genius. And that's exactly what an operon is.
So what exactly is an operon? It's a whole cluster of genes that all work together on a single task. And they're all controlled by one single promoter and one single operator. It's a masterclass in efficiency that more complex organisms, like us, just don't have. Honestly, it's the secret weapon that lets bacteria adapt to new situations so incredibly fast. Let's jump back into our smart kitchen for a second. An operon? It's like taking every single appliance you need for a big recipe, let's say baking a cake, and wiring them all to one master switch. When you flip that one switch, boom, the mixer, the oven, the timer, they all kick into gear at the same time, perfectly coordinated. One action, one complete process. It's just beautifully streamlined. To really see how this works, let's walk through two classic examples. We'll set them up as two different scenarios happening inside our little bacterial kitchen. Okay, scenario 1, the famous lac operon. So imagine the bacterium's favorite food, its main fuel, glucose, is all gone. But hey, there's something else on the menu, lactose, the sugar you find in milk. The bacterium needs to quickly switch gears and start using this new fuel source. So how does it do it? The lac operon is an inducible system, which means it's normally off. The safety lock is on. But when lactose shows up, the lactose molecule itself is the key. It floats over, binds to that repressor protein that's blocking the way, and makes it fall right off the operator. That clears the path for our chef, RNA polymerase, to start making the enzymes that digest lactose. So the new ingredient, just by being there, turns on the exact machinery needed to use it. Now for our second scenario, the trip operon, which deals with the total opposite problem. This isn't about a new ingredient, it's about having too much of one. You see, the cell can make its own tryptophan, which is a vital amino acid. But if it already has plenty, why waste energy making more? The whole system runs on a simple, elegant, negative feedback loop.
And here's the kicker. The trip operon is repressible, meaning it's normally on, just churning out tryptophan. But when the levels of tryptophan start to get high, the tryptophan molecules themselves float over and attach to the repressor protein. This activates the repressor, which then latches onto the operator and shuts the whole production line down. Get this, the final product literally flips the off switch on its own assembly line. How smart is that?
But it doesn't stop there. Beyond these basic on-off switches and operons, the bacterial smart kitchen is just packed with an amazing collection of advanced gadgets and sensors for even finer, more nuanced control. And believe me, this toolbox is deep. Bacteria have RNA thermometers to sense temperature changes. They use something called quorum sensing to actually talk to their neighbors and coordinate group attacks. Sigma factors act like a GPS, telling the chef which specific recipes to find. Alarmones are basically panic buttons for when the cell is starving. And yeah, they even have their own advanced immune system, called CRISPR. Let's just pause on that last one for a second, CRISPR, because it is truly incredible. You might know it as a revolutionary gene editing tool for us humans, but it actually started out as a super effective security system for bacteria to fight off invading viruses. Here's how it works in 3 quick steps. First, adaptation. If a bacterium survives a virus attack, it literally snips out a piece of the virus's DNA and stores it in its own genome, like taking a little mugshot of the criminal. Second, expression. It then makes an RNA copy of that mugshot to use as a guide. And third, interference. That guide teams up with a protein called Cas, and they patrol the cell. If that same virus ever shows up again, the guide recognizes it instantly, and the Cas protein acts like a pair of molecular scissors, chopping up the viral DNA and neutralizing the threat. It's a learned, adaptive immune system in a bacterium. So all of this leaves you with a really fascinating question, doesn't it? For billions of years, these tiny, so-called simple organisms have been perfecting the art of resource management. So if they can achieve this level of elegance and efficiency on a molecular scale, what can they teach us? What principles can we borrow for our own world, from designing smarter computer networks to, finally understanding the incredibly complex web of gene regulation that's happening inside our own cells right now?